My name is Brian Cunningham. I've been with ELPRO for over 10 years now, and I've been in the industrial wireless business for about 20 years now. And prior to that, I was an instrumentation expert, selling all kinds of different types of pressure, level, temperature, you name it, types of transmitters here. Now, just a real quick thing. ELPRO's been in business for 35 years now, and we've sold hundreds of thousands of radios. They've been installed around the world. And this slide just kind of gives you an idea as to some of the markets that we've sold our radios into. Radios are used just about everywhere these days. It literally does not matter what kind of facility you are. If you forgot to string an Ethernet cable when the facility was being built, or you forgot to string a twisted pair for running some 4 to 20 milliamp signals, this is where radios come in. We save the day, so to speak. So they're used all over the place. This is a summary of the ELPRO product line here. And this is how we sort of break it down when we want to describe it to customers. Now, today we're going to be talking about the Condor series of radios, which are these two guys right here, the 415U-2 and the 415UE, this guy right down here. So we're going to be looking at this guy here and this unit up here. But just if you haven't seen this slide before, this is how we break it down. The remote I/O radios, these are radios that have 4 to 20 milliamp and discrete inputs and outputs on them. The gateway radios here, these have the ability to communicate using a protocol to a PLC. So they can do things like Modbus RTU, DNP3, Allen Bradley's DF1, or their Ethernet IP protocol. So these ones usually connect to a PLC and store all the data in registers to be read using a protocol. The Ethernet pass-through modems on the third row here, these all essentially do the same thing. Whatever you stick into one radio's Ethernet port comes out the opposite radio's Ethernet port. And then lastly, we also do serial modems for RS-232 and 45 data, and we have cellular capabilities as well. And in Australia, they have a full system solutions group. We don't offer that here in North America, but in Australia, they can design a complete SCADA system for you. So again, today we're going to be looking at the Condor series of radios. That is our latest generation of radio that we have developed. And that's the 415UE and the 415U2. Here we go. This just shows you the two models we're going to be talking about today. On the left-hand side is the 415U2, and you can identify that because it's got the terminal block, the large terminal block on the front, and that's where the 4 to 20 milliamp and discrete inputs and outputs are wired to. And then we have a less expensive version, which is fully compatible over the air. This radio is identical to the unit on the left, however, it does not have that I/O across the front, and of course sells at a lower price point. What you see across the bottom here is a repeater station that we have developed, and it contains two Condor radios inside of it, and it has the ability to automatically switch over if one of the radios fails. So this is in a 19-inch rack mount enclosure. You can see we've got some fans there as well for heat dissipation. And this repeater base station will also automatically switch over to exercise the two radios. So this would be used at your head office location or at a critical repeater site, because in some topographies or some layouts of networks, if you lose a critical repeater, you will lose communications with everything downstream that repeater acted as a repeater for. So this base station repeater resolves that. This now gives you full redundancy of two radios in a single package with automatic switchover capability. Okay, so this is very typical where the Condor is being used. The Condor is a licensed 450 megahertz radio. It is also available as a licensed 150 megahertz radio. And in the next quarter, we'll be releasing a licensed 900 megahertz version of this radio. The reason I mentioned the frequencies there is obviously it's relevant to our conversation about radios, but with 450, the lower the frequency, the greater the range. So at 450 megahertz, we can get approximately 50 miles of range. And if we drop that frequency down to 150 megahertz, we can get about 80 miles of range. So what that means is that for water wastewater applications, all of your pump stations scattered around neighborhoods, even if they don't have good line of sight, the lower frequencies really have excellent object penetration ability, and they can go much, much farther than the 900 megahertz or the 2.4 gigahertz radios that we all use around our house. So tremendous range capabilities, and that's why it's very popular for water wastewater. They don't have to mount the antennas all that high. These, at this frequency, we can shoot through trees and houses and even a little bit of land. So it makes the design and layout much more flexible. Okay, so here we go, just looking at the two units side by side there. The most popular one we're expecting to be is going to be the 450 megahertz radio that we colloquially refer to as 450. It can be adjusted anywhere from 400 to 480 megahertz. The transmit power can be set up to 10 watts peak transmit power. The channel spacing, we can offer 6.25 kilohertz, 12.5 kilohertz, or 25 kilohertz wide channels. Now, in the US, you can no longer get a 25 kilohertz channel. In Canada, I believe you can still get a 25 kilohertz channel, and you can in a lot of other countries around the world. But in the stateside, we would be dealing with either 12.5 kilohertz bandwidth or 6.25 kilohertz bandwidth. Now, the bandwidth that you get is directly relates to the throughput that the radio can have. So in other words, if we have a wider channel spacing, we can have a lot more throughput. So for example, at 12.5 kilohertz, we're going to have twice the throughput available that we would have at 6.25 kilohertz. So that might be important if you're connecting PLCs together and you have a fairly steady stream of data and you need some fairly quick response times. But we can certainly use something like a 6.25 kilohertz wide channel if we're just taking a couple of 420s that we've wired into this terminal block and we're just radioing them back to this unit here that's connected to a PLC. We could easily send this data because 4 to 20 milliamp signals are generally going to consist of 2 bytes of data. So very small amounts of data for the actual I/O. But if we're going to send a PLC protocol, we're probably going to need a little bit more throughput there. So a wider channel might be a better idea. The throughput with compression, it's better than 140 kilobits per second. And this is a substantial improvement over the previous generation of radios. And I'm going to talk about those in a couple of minutes for comparison purposes. But just to give you an idea, these new radios now use Qam modulation. So that is quadrature amplitude modulation. Older generations of radios used FSK, which is frequency shift keying. With an FSK radio, the highest throughput you're able to get if you have a 25 kilohertz channel is only going to be about 19.2 kilobits per second. So 19.2 baud is pretty slow. If you take that same channel bandwidth here, our 25 kilohertz, and we now use Qam modulation, and we throw in a bit of compression, we can now get 140 kilobits per second of throughput. So that's a pretty big jump. We went from 19.2 kilobits to 140 kilobits per second by using Qam modulation. Now, I'll just give you, just in a nutshell, FSK what they do is they superimpose a frequency upon your carrier frequency. So the carrier frequency would be what FCC gives you to use. And for example, they might say, we'll give you 450.000 megahertz. And nobody else in that same geographic area will be allowed to use that frequency, and the FCC will not license anybody else to use that frequency. So with a licensed radio, you have exclusive use of that frequency in your geographic area. So, yeah, so with the QAM modulation, we're now able to get substantially higher throughput there. Oh, and that reminds me, with FSK, they modulate the frequency. With QAM, they modulate both the frequency and the amplitude, and that gives them a much wider or much better coding system, and that's how they're able to get much more data on a single carrier frequency. So now they're modulating both the frequency and the amplitude, whereas in the past with FSK, we only modulated the amplitude. And it's only in the past 10 years or so that the technology has been available, that there have been chipsets and components that have allowed manufacturers like us to design these types of products. So QAM modulation is a significant revolution in radio communications these days there. Now these are Ethernet-based radios. It's a full digital design platform. So we do have full IP communications. So it's a standardized product. I think you'll find a lot of the terminologies are going to be very common among other 802.11 based equipment. We've developed a proprietary data compression technique, and you can also support multiple data rates at the same time. And I'll jump into that. I've got a diagram that shows you, explains that in a little greater detail, so we can chat about that in a couple of minutes here. We also have something called Pearlmesh Networking, and what that allows you to do is allows the radios to figure out which units they should use as repeaters to get a message to the final destination. So what that means now is if you have radios or equipment or machinery that is moving, the radios will automatically reroute data as needed. So that's great. It also works very well when you have repeater sites that may be powered off for a variety of reasons periodically. So if you power off one repeater, Pearlmesh will automatically figure out what other radios to use as a repeater. As an option, we also have fixed links, and I'm going to show you how to set all that up in the software in a couple of minutes here. Okay. We also have the most advanced AES encryption, 256-bit encryption. Today, that is considered unhackable with today's processing and computing abilities. So that means your data is absolutely secure. Nobody can possibly get into it, unless they've got a supercomputer, which, of course, is not something that's going to be portable that your average person is going to have access to. We also have IP filtering. We've got user access control, and we've got event logging, things like that as well. And these are quite flexible radios in that we have two different versions. They can communicate with each other over the air. We also have DNP3 outstation capability. We also have Modbus TCP and Modbus RTU client and server modes, or with RTU, it's master and slave modes. So the radio has full Modbus capabilities. Okay, so just having a look at the 415U-2 for a quick minute here. When we say the C4, this refers to the frequency band. So the C4 goes from 400 to 480 megahertz, and then we have the C1, which is the 150 megahertz version, and eventually we'll have the C9, which is the 900 megahertz licensed version, etc. Now, one point I did not mention earlier that I've just remembered now is the 900 megahertz licensed version operates from a 930 to 960 megahertz, whereas the license-free 900 megahertz spectrum is from 902 to 928. So there are two types of 900 megahertz radios we will refer to periodically. The licensed 900 megahertz on the higher portion of the spectrum, and then the unlicensed 900 megahertz on the lower portion of that spectrum. So we have essentially a wireless I/O radio and a gateway built in with Modbus capability, as I mentioned before. We have built-in I/O. We have 4 analog inputs. We have 2 analog outputs, and then we have 8 DIO. So these are digital or discrete channels, and they can function as inputs or outputs depending on how you program them. As well, we can have pulse inputs going into the radio. So the radio will accumulate pulses, transmit those values to the opposite unit, and it'll either store that pulse count in a register, or it will replicate that pulse count and deliver it out a pulse output. So we can handle all the common types of I/O that we run into in the instrumentation world. As well, we have a series of expansion modules that can connect to this radio via RS-45. And you can have up to 32 expansion modules connected to a single radio. And these expansion modules, we have 3 different versions, one with all analog inputs, another with all analog outputs, and then a third one with discrete I/O. So you can literally have hundreds of inputs and output points on any of these radios. So it's very easy to expand the I/O points of this type of radio here. Okay, so the main applications, we see bore and portable pump control applications, monitoring reservoirs, elevated water and petroleum storage tanks, as well as just connecting to any type of instrumentation, really. If your instrument is a couple of miles away from the main plant, maybe you're monitoring the temperature of effluent before it's dumped into a river, or you're monitoring river temperatures to make sure you don't dump too much hot water into the river and kill the fish. Any application where an instrument is some distance away from a plant, that's where these radios come into play. Okay, the 415U-E radio, we say E for Ethernet. That's the base of the radio, or how it's designed around. We have 2 digital points on this radio there. They can be inputs or outputs, but we have just 2 of them on the radio. And to make life a little bit simpler, if you want to know what the signal strength is, you can just look at the LEDs on the front of the radio. The more LEDs that are on, the stronger the signal is. Okay, and again, same sort of features as the other radio there. Full Modbus DNP3 capabilities. We can have bridged or routed IP traffic, and the main applications for the 415UE will be with PLCs, RTUs, HMIs, flow meters, SCADA computers, any industrial communication, any industrial machine-to-machine communication is where these are used. Okay, now we have the Condor base station repeater. As I discussed earlier, it has 2 radios inside to provide redundancy at a critical point. So you may wish to have one of these radios as your master unit. And in this diagram, we see the master is communicating directly with a couple of remotes. And then we can see that we have a remote radio here, a remote base station repeater that is servicing another 5 remote sites. And if you're serving 4 or 5 remote sites, if communications are critical, and usually they are in the water wastewater business or electrical utility business, that's where you might decide maybe we do need that redundancy to get us that level of reliability. So some things it'll monitor will be the actual radio itself. It'll look at the power amplifier temperature, the PLL, the phase lock loop, and make sure that's functioning properly. It also monitors the antenna to see if the antenna is providing proper impedance matching to the power amplifier. And of course, it also monitors the microcontroller and the power supply. So there's a bunch of other features that it monitors as well. I think there's about 10 or 12 different parameters, but those are the most critical ones here. So just to, again, talk about the development process that we went through over, I believe it was a couple of years to develop a new radio. Developing radios is not simple technology. It is highly advanced. It's probably among the more advanced types of instrumentation that I've encountered out there. But we have full DSP, digital signal processing engine, provides very high performance and much better configurability. Typically in the past, it was very difficult to build a single radio, a piece of hardware, a single radio model that could cover a very wide range of frequencies. So you would have radios that came in 20 or 30 megahertz bands, and you'd have to stock a lot of different models. But now with DSP, we have a very wide tuning bandwidth, and that's reduced the number of radios we need to keep in inventory. Ultimately, it reduces your customer's cost, because if we can lower our cost, that usually gets passed down to our customers. So tremendous amount of effort went into designing this as well. It's also worth mentioning again the over-the-air context-based data compression. Again, it's a proprietary technique that we have developed, and it essentially improves end-to-end throughput. We do have some advantages over our competitors in this data compression. We compress the entire packet, including the overhead. For some reason that I'm not entirely clear, our competitors do not compress the header. If they have compression, they only compress the actual data packet, and that is not quite as efficient. So here we go. This kind of just shows you the throughput that you can get with these radios here. And I'm not going to go into too much about some of this stuff, but I'll tell you some of the things. FEC stands for forward error correction, so we can apply that to the signal to correct any missed packets or missed bits. But just gives you a rough idea of the throughput that we can get. Keeping in mind, as I mentioned earlier, the wider the frequency channel, the higher the throughput is going to be, and it's directly correlated. So you can see the throughput doubles when we double our channel bandwidth that we've been given. Okay, so here we go. We're showing some of the older radios, FSK, frequency shift keying right here. 19.2 kilobits was the fastest we could get. Now we can get up to 140 kilobits per second. So, oh, here we go. This is just showing the raw data throughput, and this is showing with compression. This is the improvement that we get. We go from 96 kilobits per second raw data throughput to 140 using our compression technique. Okay, so it just gives you rough ideas to what sort of throughputs to expect there. Now I just wanted to talk about typical distances that you can get with a 450 megahertz 5-watt radio. And this also highlights that the antennas need to be mounted higher and higher in order to get longer and longer distances. So if we have just a 2,000 foot distance, densely obstructed, so that's mean trees, houses, maybe a little bit of land in between, we could do it with just a fairly small omnidirectional antenna. This guy's about 2 feet tall, and we mount the antenna 10 feet above ground. We're good to go. As soon as we get to about 5 miles, that's the cutoff point where we need to have line of sight. And at that point, we should also use a higher gain Yagi antenna. This one's about 3 feet long, I think, in that range. And we're going to have to mount it fairly high above ground to be able to get those types of distances here. So it just gives you typical distances. These aren't hard and pat rules They're just guidelines to let you know what is typical and what can be fairly easily accomplished. Okay, so again, just wrapping up some of the major release points. I'm going to jump into the software in just a minute here. And let's see, we've got this one is the automatic data rates. So what it does is if you have one remote radio that is very close to the master and the signal strength is very strong, it will use a faster modulation technique and it'll get higher throughput. And if you have a more distant radio where the signal is very weak and the radio has to use lots of forward error correction, which slows throughput, it will use a lower data rate to communicate with that remote radio. So that allows you to essentially optimize the network. The radios that can communicate fast do, and the radios that can't drop down to their lower data rates there. Okay, we've also got this Pearlmesh networking method where the radio network will figure out which ones to use as a repeater. We also have IP filtering in this radio, and what that does is that blocks traffic that is not destined for a remote radio from getting into the radio network. So oftentimes we'll have a setup where we have, say, a radio connected to an Ethernet switch, and the switch also has a PLC and an HMI that are chattering back and forth. Well, if the radio sees all that traffic, it'll just blast it out over the air unless it has IP filtering. And then we can make sure the traffic that is not destined for a remote radio it does not get sent over the air. So we do the IP filtering, and I'll show you how that's set up in a couple of minutes here. Then we have something called I/O+. And what that is a simple logic structure inside of the radio that allows you to do simple if-then statements or counter or timer statements. So very, very simple logic capability has been built right into this radio. So in a sense, this is replacing a PLC for very simple applications at some remote sites. Okay, then we also have some diagnostics. We've got logging of the IP traffic to local memory, event logging, all that kind of stuff to have a look at there. So this is just showing you one of the setup screens. There are two methods of programming it. One is by using the web-based configuration. That's generally more done so for diagnostics. And then we also have a Windows-based software program, which is generally the most popular starting point. So that's where you would say, I've got a network of 10 radios. I'm going to configure everything on the software. And once I've finished configuring, I will download all that information into each radio. Here we go. This is just showing you what I was describing, the different data rates that the radio can use. So depending on the strength of the signal, if this one here has a very strong signal, it can use 64-bit QAM modulation, which gives you the highest throughput. This one here, if it has a weaker signal, might use a different modulation technique, which gives slightly lower throughput, but still allows it to maintain the link. And this one here might be right in between, so this one might have a middle level of throughput. So the radios communicate with the master radio communicates with each remote at the fastest possible speed that the signal strength will allow for. So that describes it in a nutshell. Okay, and here we go. This is illustrating the Pearlmesh concept here. So this is ideal for mobile applications where machinery is moving around and radio paths may change. If this remote radio right here, if it cannot shoot direct to the base radio, then it will use one of these two guys as a repeater. And if one of these two guys is not available, it'll automatically figure out what path is ideal to get the signal back to the base. So it's a meshing type of protocol, which just refers to automatically determining what radios to use as repeaters. So when you're deciding whether to use Pearlmesh or whether to use fixed links, Pearlmesh is designed for smaller systems up to 10 units. And that is generally because it uses a little bit of overhead to figure out which paths are ideal. So there's a fair bit more overhead involved in a Pearlmesh network, and that's why we limit it to 10 radios. Fixed links, I'll show you how those are set up, but generally if equipment is bolted down and it's not moving, like it's a water storage tank or pump station or something like that, fixed links works great. It allows you to build a very large system, and you can still set up roaming for some remote stations if you like. It's still possible to do that, so you can set up alternate paths. But these are where we know 99% of the time there's only going to be one radio path getting back to the base station. So we would use fixed links in that scenario. This one here just shows you the setup of the I/O plus logic ability here. And it shows you some of the statements that you can create. So for example, you know, this loads a value from this register. So this is an analog register, so it loads the value from it. Then it says if that value is less than 8,000, do a jump and that sort of thing. So it looks like a very basic, if you programmed PLCs before, this is going to be a piece of cake. And we've got some application notes to help you get through it. Now, one other unique capability that we've provided in the radio is the ability to set up a dashboard. So what this allows you to do is you can log into a remote radio. So you take an Ethernet cable, you drive out to that remote site, you plug into that radio, and you want to see what the 4 to 20 milliamp signals coming into the radio and what the discrete signals are all doing to troubleshoot it. Well, you just plug into the radio and you pull up the dashboard, and now you can see exactly what the what's happening with the 4 to 20 milliamp signals, and you can have them converted into engineering units. So in this case, it's measuring a reservoir. The reservoir is taking a 4 to 20 milliamp signal that we have converted into engineering units by telling it what height is 4 milliamps and what height is 20 milliamps. And this one is now telling us the reservoir level is 4.5 meters high. And we can do the same with all these other different parameters, and it makes it much easier to troubleshoot. Now, this can also be viewed over the air. So if you plug into the base radio and you pull up the configuration menu for a remote radio over the air, you can also access this information over the radio network. So it's very interesting, it's very cool, and allows you to very easily see what all of your 4 to 20s and discretes are doing. So this is what things, on the right-hand side, this is what things have historically looked like. We would have a PLC, we would have a radio, and we'd have to program the two devices and get them all communicating and that sort of thing. Or we can just have a single radio that has that the 4 to 20 and discrete inputs and outputs, and it also has some basic logic on board. So unless you're doing very sophisticated control, you no longer need to have all of this equipment in the panel. You can just have a single radio there. Okay, now if we do have more sophisticated control and logic taking place at a remote site, we can just use the 415U-E at a lower price point and then combine that with a PLC. So tremendous flexibility, tremendous capabilities in these devices here. Okay, guys, so we finished the this session of the training. So I'm going to jump into the software and show you how to get things set up here. Okay, so let me just find our software here. Let's just have a look here. Okay, and here we go. So you should be having a look at our device configuration utility software. So this is a Windows-based program, works on Windows 7, Windows 10, and that's about all the platforms I'm familiar with. And it's free to download from our company's website. So what we would do is we would start by creating a new project, and we'll just select a project name. I'll just call this project 155 because I've done this quite a few times here. And there we go. We've started our network here. Okay, so the first thing to do is we need to add some radios to the network. Now, let's say that we had an existing network and we wanted to pull the configuration out of it. Then we would select load a new unit, and that pulls the configuration out of a radio and displays it in the software here. For now, we're just creating the project file, and once we have created that, then we'll go ahead and download that to all the different units. So we have to tell the radio which model of radios we have. In North America, we're going to have just these two guys right here. We also have an Ethernet expansion module that is used with this software. So I'll start by selecting a 415U-E radio. Okay, there we go. We can see some of the options for that radio. I'm going to add a couple of other radios to the network as well. The remote radios, let's say we've got some 4 to 20 milliamp signals we need to connect to them. So we will select the 415U-2 as our remote radios. And I'll add just one more for good luck. Okay, and here we go. So these are all of our radios here, and I'm going to change the names of these radios a little bit to make them easier to understand. We're going to call this one our base radio, so our master unit, base unit, whatever you like to call it. We're going to call this one, we're going to call it a Pine Street pump station radio. We'll pretend this is a municipal application. And we'll call this one Spruce Street. And we'll call this one Oak Street. Oops. So as you can guess, here in Vancouver, they like to named a lot of the streets after trees. So what we do is we start with the base radio, and we decide what networking mode we would like to use here. Okay, we have the options. We can manually set the radio up. Okay, and this is just telling me that it's part of a network. So if I change the networking mode, I'm going to have to program all other radios. Okay, so with the manual mode, we have access point and client stations. So I would just tell it what function this particular radio is going to have. And then we can see we've got the SSID, encryption, etc. And these parameters must be the same on all radios. And the good thing about the software is you don't have to copy all that over. Once you set one radio as an access point and set the SSID, all other radios have the same settings. Okay, so that's assuming we want to have a manual network there. And once I set this radio, this base radio as an access point, if I click on the other radios, and I also set them up, oops, okay, they can only be clients. So there can only be one access point in the network. Everything else needs to be a client. Okay, if I go back to our base radio, and I change that to a Pearlmesh network, Then I have just two possible operating modes for radio. I can have the base radio or base or master radio, or everything else becomes a mesh node. So there's only one base radio, and that's the head end where all the data needs to get to. Everything else is a mesh node and will act as a repeater to other radios if needed. Okay, so with the Pearlmesh, very simple setup. You just assign one radio as the base unit. Everything else becomes a Pearlmesh, and then you don't really have to set too many other parameters there. And then lastly, we have our fixed links, and this is where we have a network where we're not expecting units to be moving around that much, but we occasionally may need a radio to act as a repeater. So we have one radio will act as the base unit. Then I'll go to the next radio and I'll set it to the same fixed links here. And the next radio, I'll set it as a repeater. And you have to tell it what is the upstream radio that it will always need to communicate with. And in this case, we'll say it's our base radio. So the Pine Street radio is going to act as a repeater, and it's always going to know that the final destination for all data that it's repeating is going to be this base unit up here. Then if we go to the Spruce Street location, and we set our fixed links there, then this one can be a remote. Okay, and since it's a remote, we have to tell it what's the upstream device that you're going to communicate to. Are you going to be using the Pine Street radio as a repeater, or will you be shooting directly to the base? Is it possible to shoot directly to the base? So this just tells the network with these fixed links, where are you shooting to? And this makes device configuration so much easier than in the older days where we would have to do all kinds of setup and configuration to enable this type of capability here. Okay, so we've talked about that. The three different operating modes. We've got the manual mode, Pearlmesh, or fixed links. And generally Pearlmesh and fixed links, those are going to be the two most popular because they look after a lot of the setup for you. Okay, then we have our encryption. We offer two types of encryption, AES 256-bit or WPA2. I usually just use AES 256-bit. Again, as I mentioned earlier, it's considered unhackable by today's computing standards. Now we have to enter a passphrase. So, you know, whatever you want to type in there must be the same on all radios. Okay. One thing I haven't mentioned here is there might be a case where this remote radio could be roaming around, and it might communicate with either of these two devices here. So if that's the case, then I select roaming. If I deselect it, then I have to tell it specifically which other radio is upstream, which radio is closest to the base where all data is going to end up at the end of the day. Okay. Okay, so that's sort of the wireless interface, the networking mode and explanation of that. Then we have the radio setup, and we have the modulation mode. Now, we have an older generation of radios that do FSK, and if this radio were to be inserted into a network of older radios, then we would have to downgrade this radio to use the older over-the-air communication protocol. But if it's a new network, we would select QAM to get the optimal throughput from the radio. Okay, then we have a bunch of different licensing bands here for all kinds of different countries here. We've got a bunch of US bands here. But sometimes I just go ahead and select this one here, licensed worldwide. It says it excludes the US, but you can still set it to the US American settings. It just allows you to set it to a couple of bands that in the US are not permitted for this purpose. But if I set it to the FCC band 1, you can see that the maximum frequency is 454, the minimum frequency is 421. If I select band 2, you can see the max and min frequencies change. And then I can go to band 3. Again, they change a little bit further, and same with band 4. They change a little bit. So whatever license you get from the FCC, just give it a try, select one of the bands, see if it covers your band, and if not, select one of the others there. Okay. Then we have the bandwidth. So this is how wide of a frequency channel the FCC has given you. And there's really only two options in the US. 12.5 gives you more throughput. So if we had PLC to PLC communications, we probably want this guy here. Otherwise, if it's a low throughput application, we could get away with the 6.25 kilohertz wide channel. Okay, then we have these two parameters right here. We have the radio base, and then we have the radio transmit data rate. And the radio base is used for sending out beacons. So this is the overhead. So this is when the radios are establishing communications, what baud rate are they going to use? The lower the baud rate, the greater the distance you can get with these radios. So that's why we have these selections here. Now, I could set it to the lowest possible data rate, and that would ensure that I can communicate with the most distant radio. But if your radios are going to be all within reasonable range, using this lower data rate uses a fair bit of overhead. So that means we're using, let's say out of a 1 second time slot, we might be using 400 milliseconds just to send the overhead. Whereas the actual data, if we can send that at 24 kilobits per second, the data is going to be sent extremely quickly. So we don't want to use too much overhead to send out the beacons, too much bandwidth for the overhead. So that's why we generally select a value of 8. Seems to work for most applications. For the transmit data rate, this is your actual user data going back. This is the PLC communications going between the two radios. I always set it to auto. And that way the radio will determine the fastest possible data rate. And if it can't do it at 24, it'll do it at 16. If it can't do it at 16 kilobits per second, it'll drop down to 8, et cetera, et cetera. So the radio will figure out the fastest possible data rate. So that's the difference between these two guys here. This is for the overhead for sending out beacons and establishing the radio link. This is your actual user data that's going back and forth. Okay, then we have the transmit power level. It's expressed in dBm and converted into watts right here. So pretty common power level is 36. And as soon as we click to the next box, you can see that's 4 watts of transmit power, that sort of thing. And then we have our transmit and receive frequencies. Usually these are the same, but in some applications they can be different. So the radio can transmit and receive on different frequencies. Okay, and then we have the IP address that we assign to this radio here. So this is what we use to communicate when we plug in by Ethernet, or if we go over the air. We type in this IP address into a browser and the configuration will pop up. Then we have our filter settings, and we call it our easy filter because it's dead simple. So this is the first device IP address, and this is the last device IP address. So all we do is we make sure that all of the PLCs, all of the RTUs, the HMIs, all of the radios, anything that needs to communicate together are all on this IP list. And if a message comes into the Ethernet port that is not destined for one of these, an IP address in this range, it is blocked. So that prevents data that is not intended for a remote device over the air from the radio transmitting it and therefore clogging the bandwidth of the radio. Okay, so up here we've got just some usual options here. When we're ready to program all these radios and we have everything all set up, we click Program Unit. And there's two methods of connecting, Ethernet or USB, or we could do it with an XML file. But what we have to do is we have to tell the software what the IP address of the radio is that we're going to be sticking the data into. So in this case, this radio has an IP address of .101, so we just make sure that that IP address is printed up here. Then we enter our user and password, and we hit program, and presto, the configuration is sent from the computer into the radio. Okay, this function does the opposite. This pulls the configuration out of the radio and into the software. Okay, and then we have some other things. We can monitor communications. We can go to I/O Diagnostics, where we can see what each 4 to 20 milliamp input signal is doing, etc., etc. Okay, now I'm going to show you a whole bunch of other options here, and I think what I'll do is I'm just going to kind of give you an overview, enough to kind of make you dangerous and maybe get you started on a project. But you can see there's an awful lot of options here, and we're not quite going to have enough time to review all of them in full detail. So what I will do is talk about the most important ones here, and I'll head down to one of the 415U-2s because they have a lot of I/O on them. So these are wireless mappings. So this is how I transfer a 4 to 20 milliamp or discrete signal or a block of registers from the Pine Street radio back to the base station radio. So we have some different types of mappings. We can do a write mapping or a read mapping. And then we also have a gather scatter, and that takes a bunch of different non-consecutive points and sends them in a single transmission. So I'll just show you a write mapping. We select the destination radio. In this case, I want to send it to the base radio. This is the I/O count, how many data points. Maybe I want to send all 4 analog inputs. And this is our update time. So this radio will transmit every 10 minutes unless any of those 4 to 20 milliamp signals change by more than half a milliamp. And we have something called a sensitivity block, where we can determine how much of a change in that 4 to 20 milliamp signal has to occur before this mapping takes place. So then we have, these are all the I/O points on board the radio. I mentioned I wanted to send analog inputs 1 through 4. So I select those guys there, but you can see we've got analog outputs, floating point, formats, etc. And then the destination. Where do I want to send these radios to? Now this base radio does not have analog outputs, so we just we would send it to a generic series of registers. So these radios use Modbus register addressing format. So holding registers are in the 40,000 series of registers there. So we're going to take the analog inputs from one radio and store them in a block of holding registers at the base radio. And I'm going to type in a name up here as to the function here and this sort of thing. And then we also have a really cool feature, which is this acknowledge. And this allows me to ensure that this mapping took place and that everything is working okay. So what I can do is I can use a digital output on the radio, and this output will remain off if this mapping was successful. So the radio sends a mapping to the base radio sends an acknowledgement back. If this radio got the acknowledgement back, this output will be off. But if the mapping failed due to a broken antenna, lost power, something like that, then this output will turn on. And there is an LED right next to each digital output. So by setting up a bunch of mappings and using these acknowledge failed registers, I can determine if these wireless mappings were successful by observing the LEDs. So it's a technique that I've used to help troubleshoot the network. Okay, so there we go. That's how we send a block of radios. Now we're running out of time here, so I'm just going to give you a quick summary. The networking, this is just where we set the IP address of the radio. We have an RS-232 port and an RS-45 port. They can be used for independently. They can be used for Modbus RTU master, expansion IO, Modbus RTU slave, or as a serial gateway. The 45, we have the same options. Then we have our Modbus setup. We can have Modbus master or Modbus slave modes set up on this radio. You can do it the 232 or the 45 port. And then we have our I/O, digital inputs and outputs, just allows you to scale the inputs and outputs as needed. Then we have our fail-safe blocks. So these allow you to set initialized values. So when the radio powers on, you can have all outputs be off. As well, if radio communications are lost, if an update is not received within a certain time frame, you can have the values go to a default condition, like the digital outputs. Maybe you want to turn pumps all off if you lose communications, or with 4 to 20 milliamp signals, we could maybe have it go to 2 milliamps so that you know that it's a fail condition, but it's not a broken wire condition. And here we go, the DNP3 settings, and then lastly is that dashboard that I talked about. And here's where you would set up the dashboard so you can view your inputs in engineering units. So this is where we type in, maybe it's pressure, we type in the units, could be PSI, and then we enter in high and low values. In other words, 0 milliamps corresponds to what pressure, and 20 milliamps corresponds to what other pressure. Okay, and that's pretty much it. So I think I've hopefully given you a good rundown on these the devices here. And we're pretty much right on 10 o'clock. So Matt, can I see if we have any questions here?
Yeah, Brian, we got 2 questions that came over. First one's regarding the base station repeater. Question was, does the backup 19-inch solution, base station repeater, automatically fail over and then fall back if the primary radio is recovered?
Yes, that is correct. Yep, it will, if the alarm condition is removed that caused the radio to switch over to the secondary radio, then it will continue to exercise the primary radio. So these radios switch over. They usually have a duty cycle. I'm not sure what it is, maybe 10 hours or something like that. And then they switch over to the opposite radio. So yes, it would resume operation if those errors cleared.
Perfect. And the second question regarding the auto mesh capability. Question is, how do we suppress mesh radio storms when we're doing an auto mesh?
How do you suppress a mesh radio storm?
Yes.
I'm not really familiar with what that refers to. I can tell you that our Pearlmesh is something that we have developed in-house, specifically because we needed to make sure that the radio's overhead would not overwhelm the bandwidth. Because these are not Wi-Fi, high-speed Ethernet modems, we have to make sure that the overhead is not going to overwhelm the network. And that's why we limit the network size to approximately 10 units. But I think a mesh storm is referring to a whole bunch of radios all being powered on at the same time and all trying to relink to each other. That's something that we have developed into our Pearlmesh protocol, specifically designed for low bandwidth radios. So that is not a condition that's going to occur with these types of radios if I follow the definition correctly.
Okay. I'm guessing that when it's in the Pearlmesh functionality, it's going to reach for the neighbor radio that has the strongest signal. So if it can identify two other radios within the network, it's going to attach itself to the strongest signal. Would that be a safe assumption?
Yeah, yes, correct, absolutely. As long as that, the second part of that is as long as that that repeater now has a path back to their base unit.
Okay. All right. That's all we have for questions at the moment, sir.
Great. Well, hey guys, thanks for attending, and we've got another great seminar coming up in 2 weeks' time, and we will have this on YouTube, as we did record this session today. So again, if you have any questions, Matt and Tim both know how to get a hold of me as well. You can feel free to contact me directly.